7, so we have been until 8, not 7. So
Nuclear fusion can be defined as the bonding of two smaller nuclei to form one larger nucleus. For the context of this presentation, the standard fusion reaction is the deuterium-tritium reaction, which is the one currently selected for fusion energy generation. Nuclei are held together by binding energy, which is much stronger than electronic bonding energy. This nuclear binding energy is the reason we can extract so much energy from fusion. So you might wonder why hydrogen and helium. The reason is that to fuse nuclei, atoms need to overcome repulsive forces. Larger atoms require higher energy inputs to achieve this. As I mentioned before, to generate a nuclear fusion reaction, we need to overcome the repulsive forces between nuclei. This is known as the Coulomb barrier. And there are two main ways to overcome it: increasing the energy of the system or lowering the Coulomb barrier. In this slide, I will go through some important examples of reactors. For accelerating fusion, we have linear reactors or LINACs. They are from Helium company. The fusers, they are mostly for research and development, not for energy production. In thermonuclear fusion, we have the magnetic confinement. This is the tokamak. And in inertial confinement, we have this is the Peebles field, and they are both into the commercial pathway. So after all I told you, you might think fusion is so hard to get in Earth and also too costly to develop. So why should we have fusion energy? So some reasons are because of the resources availability, no long-lived radioactive waste or greenhouse gas emission, millions of times more energetic than chemical reactions, limited risk or proliferation, no risk of meltdown, and many experts think fusion is the future of energy because of the resources are available on Earth for millions of years.
before a fusion reactor becomes online, it must first satisfy the Lawson triple product criterion. This determines the minimum performance that a reactor must reach before becoming operational. Examples of this theory being implemented can be seen in the JOT, Joint European Torus, in 1983, Lawrence Livermore National Laboratory in 2021, and National Ignition Facility in 2025. And by 2027, a company out of Devon, Massachusetts, near MIT, has committed to ensuring that an operational nuclear fusion reactor will be developed. This is called Spark Tokamak. This fusion reactor will have Q is greater than 1, meaning it will produce more energy than required to sustain it. Alongside this, in southern France, since 2007, a group of countries have committed to a project called ITER, I-T-E-R. This is an ambitious task to develop a nuclear fusion reactor that will provide accessible electricity by 2047. There are two deadlines that are coming up of ITER. In 2034, they hope to have their first deuterium-only operation. In 2039, they hope to demonstrate an instance in which 50 megawatts of heat can generate over 500 megawatts of heat. This is Q equals 10, termed burning plasma. By the mid-2030s, countries across the world hope to have commercialized and operational examples of nuclear fusion reactors on their soil. Countries especially like China, Russia, and France. Nuclear fusion must first meet the base price to be commercially feasible. When I say base price, we're talking about the base price of nuclear fusion with respect to the levelized cost of electricity. In this case, this is $50 per megawatt hour. Deuterium is the backbone of every nuclear fusion plant. Deuterium is readily available, it's found in seawater, and it's nearly unlimited. On the other hand, tritium is a much more precious material, and it's a material that many nuclear fusion reactors hope to have a capacity to self-produce. The cost to develop, maintain, and refine a nuclear fusion reactor is astronomical. ITER was originally surmised to be around 5 billion euros. On the other hand, the actual cost of ITER in 2024, whereas the original markup was in 2006, has gone from 5 billion euros to 25 billion euros. ITER is still undergoing extensive construction. A viable alternative to ITER is being developed by the U.S. Department of Energy. The fusion reactor called FOAK, first of its kind, is being marked at a total cost of $5 to $6 billion, with around $3 billion coming from the Department of Energy and other public sector organizations, whereas $2 billion is also planned to come from the private sector. The primary federal program tasked with ensuring that nuclear fusion soon becomes commercialized is called the Milestone-Based Fusion Development Program. Around $46 million has already been dispersed from this program since its inception. The recipients are in 8 different U.S. states, and this dispersion has come over 18 months. This program is the first of its kind to ensure that the private sector reliably invests in the capacities of nuclear fusion, and the unique aspect of this program is that entities are only awarded money after they verifiably meet and achieve the designated tasks. The most important part of the Milestone-Based Fusion Development Program is the Part 30 over Part 50 statute. The Part 30 over Part 50 statute ensures that numerous cost regulations implemented by the NRC are removed, ensuring that commercialization of nuclear fusion can be maintained and can be increased at a steady pace. The Milestone-Based Fusion Development Program has received funding from 7 major bills over the past 6 to 7 years. The most significant funding comes from the 2 following bills: the Energy Act of 2020 and the CHIPS and Science Act of 2022. We hope that these 2 bills can serve as the template for far more funding to come in the years to follow. Thank you.